So today I'm going to show you how I study when I'm in a time crunch. This is a new method I have derived ever since ChatGPT came out. It helped me with my undergraduate final exam. I got like a 4.7. That's my best score in my entire life. I'm not even going to lie. I was so happy because this just made my work so much easier. I understood the course content so much quicker because we all know how uni is. The professor is not trying to teach you; they are just there to do whatever they want to do, and they will just go. They expect you to know these things, but you don't know these things. That's why you're here. Anyhow, let me not even continue talking. So the first thing I always do is that I get the entire course content. I have paid ChatGPT, so I do not know how it works for free. This video is also going on YouTube. I kind of know Twitch is not because I'm streaming on Twitch right now, and Twitch is not like from me. It doesn't have like a lot of streamers. Most of the streamers are doing IRL, all these fun things. So this is not like fun. This is for people that just want to get down and dirty. So we are going to get down and dirty with this. So the first thing I always do is that I put the entire course content, like I pick one chart. If you have paid ChatGPT, you don't have any limit or anything. So I put all the course content. This is the hard part, step by step. But once all the course content is here, the next thing I'm going to do is, as you can see my prompts, I'm like, give me the Word document with module because the course I'm doing module 1 to 6 with every section in it. And ChatGPT is like, just to confirm, before I generate the Word document, would you like the document to be formatted as a structured study guide with section heading, e.g., module 1, introduction, question, summary, answer for all the sections like we done? I kind of did some pre prompting. So I actually started this whole chart like July and I ran out of time, so I left it and now I'm back to the chat again in August. So the first thing I told you was make summary of the video of this. Then it made like a summary. So I think how partially to make sure I create the most complete summary, could you confirm if you'd like a concise paragraph overview, bullet point breakdown of key ideas, or both? I was like, whichever is necessary, make the summary like question and answer. Then I kind of prompted it again. I think I prompted it again. Okay, no, it just kept on giving me question and answer. So now I'm going to prompt it again. Before we get to that, I'm going to show you the course that I'm doing. I'm doing an embedded system course. I'm planning to do my master's in like embedded electronics and computer engineering, which was what I did in uni. But in the electronics and computer engineering space, there are so many things there that you can do in case someone is like trying to get into this field. So you can either like this is final year, they ask you to choose between software or hardware. So if you choose software, you're practically going to be doing software engineering. You're going to enter the AI route. You're going to enter the web dev route. Just the normal things that even computer science engineers do. But if you choose the hardware route, you're going to be doing like networking. That is like, you know how they put cables under the ocean so that you can get network to access the internet. That whole thing, you're going to do it. You're going to do something like embedded systems are also there. You're also going to do hardware. Like you can also branch into computer hardware. That is like you build CPUs, you know, gamer CPUs. You can branch into that. I have a friend that actually does that. Not a friend, a classmate that actually does like computer hardware. They build CPUs and stuff. They enter that route. I also know someone that entered the networking route, like full on networking. They are almost like electrical engineers type of networking. So, and I also know people that are doing the full software, like their full title is software engineering now. I'm trying to do embedded systems engineering software, embedded software, because I want to like I like AI and I like I'm already building AI models right now. I'm building AI models. But I also think that AI models with embedded systems is like where this whole AI thing is going to end up being so much more useful to people and so much more practical, not just the software part, but like the software with your hardware. Like imagine a lot of the things I'm talking about, a lot of people have already implemented it. So I kind of feel like I'm running out of time. I'm not going to lie. I feel like I'm running out of time. Like a movable table, a a switch that's there's already an induction oven already. So imagine like before it short circuits, you can use like AI to check, okay, is it about to like blow or something, and then the whole system shuts down on its own as a prevention measure. I feel like there are other applications we could do with this AI thing that would make our lives so much easier, make our jobs so much easier. And I want to find out like how to do embedded systems so I can like combine the two, you know. So I've done embedded systems before. We did the part of our EC course, but um we did it as part of our EC course, but I want like a certificate because I have like a Coursera certificate for machine learning that I've put, because I noticed that most of the people that are like pros in this field have one MOOC certificate or the other. So I was like, I'm going to copy them. So I got a machine learning certificate, I put it there, even though like I kind of taught myself machine learning. Then I'm trying to get this embedded system certificate, put it there. But I was like, why not just like, instead of only doing this, why not just like make video for people that are trying to also do this course too, or trying to do the same thing I'm doing. So I copied the transcript. You can also download the transcript here. Same thing with Udemy, they have the same transcripts under for people that cannot like um for deaf people, so they read it. So benefit of accessibility, it makes my work easier. So I copied all of that. So I was like, so let's go back to the last part where it said, just to confirm, before I generate the Word document, would you like the document to be formatted as a structured study guide with section headings, question and answer? Da, 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 da. I said yes, and the explanation should be simple to understand, but have every detail of the transcript in it. It's rough, but ChatGPT always understands. It's my boy. My boy understands what I type. See, I didn't need to explain myself. So it's going to let me know when it's ready. Now we're going to be watching the course while it provides my summary. But usually I read like the summary for the chapter before I watch the video for the chapter. But the beginning videos are so simple. We will need to do that. I don't know if this is copyright, but I'm not getting paid for this shit. So whether they sue me or not, I don't care.
An embedded system is a specialized computing system with hardware that is based around a chip. This could be a microcontroller or microprocessor. Its embedded hardware will vary depending on what the system is designed to do. There's no ultimate set of operational capabilities for an embedded system, but there are a few things we can expect. Embedded systems usually have hybrid processing and computation capabilities. They are typically designed to perform a well-defined task which repeats, either periodically or spontaneously upon a trigger. These task-specialized designs might interact with larger systems and the surrounding environment. Finally, embedded systems have a low power budget and relatively high performance, and a low cost. Embedded systems are often subject to real-time computing constraints. A real-time system is a system that guarantees a meaningful output is produced within a defined short period of time or interval. This means embedded systems must respond quickly to sequences and combinations of events, and typically must perform multiple separate activities at the same time. Furthermore, because many embedded systems must operate independently for long periods of time, they must handle faults without crashing. This often means that the fault handling code is larger and more complex than the normal case code. Consequently, embedded systems perform diagnostic functions to help service personnel determine problems quickly. Now, let's look at the differences between a CPU, an MCU, and an embedded system. The microprocessor, also known as a central processing unit or CPU, is the central core of an embedded system. It is a multi-purpose, clock-driven, programmable electronic device designed to perform arithmetic and logic operations using an arithmetic logic unit, or ALU. It usually performs the instruction cycle of fetching, decoding, and executing.
I'm sure a lot of
The
you,
microprocessor
heard
also
this
communicates
fetch,
with other
decode,
external components with a memory
process, like
unit
from your computer
via a memory
science in
interface
secondary
and can
school.
perform I/O
So
operations based on specific
same
instructions.
kind of thing. There's also
A
bus,
microcontroller unit,
system
or
bus, like you
MCU,
did,
consists of a
there's also system
microprocessor
bus,
plus
like we
additional
did in
peripheral
secondary school. All
components
these like
such as
little
memory
things,
blocks,
the
digital
analog
IOs,
inputs, digital
analog
inputs.
IOs,
I don't know if they
timers,
taught you guys the same
and
way they
other
taught us,
basic
but
peripherals.
like they taught us all these
The
things in secondary school, the
microprocessor is usually a
peripherals.
single-core
The same
CPU
things
to
they taught
optimize
you about
power
like your
and cost
main
efficiency.
CPU, like the big CPU,
On-chip memory
kind of
components,
applies to
such
your
as random access
microcontroller.
memory and read-only
And that's kind
memory,
of crazy
are
to me.
also optimized for speed, cost, durability, and energy efficiency. Additional hardware components can include a variety of input and output
Interrupts. Oh my god!
components,
Like I remember
timers,
when we were reading
interrupt
interrupts
structures,
in school.
external
Interrupt,
buses,
timers,
and so
input,
on.
output.
These are chosen based on the controller's final
Kind of forgot
purpose.
that part.
All the components within a microcontroller
They like
communicate
kind of
via an
control
internal system bus.
the system.
An
and when
embedded
you want to,
system
like,
usually contains one or more interconnected
around,
MCUs. Most parts of an embedded system are electrical components. However, the mechanical structure, or the housing of the sensor, may also provide important functionality. The range of applications for an embedded system are enormous. For example, an embedded system can be used as a closed-loop control system to monitor and process a system's state, or adjust an output to maintain a desired set point, such as temperature, speed, or direction. An embedded system can take over very specialized functions as part of a larger system, such as fault handling or networking, or it could be used to step through different stages of a program based on environment and system requirements. Let's look at a real-world example, a bike computer. The bike computer senses wheel rotation and outputs the calculated values, such as speed, distance, and time. Additional sensors, such as a heart rate monitoring sensor, could be connected to such a system. The system is constrained primarily by size, cost, and battery life, which translates into power consumption. This means that the total system must be very cost and power efficient. Fortunately, size, weight, and cost are usually proportional, and the only counteracting variable may be the processor performance. The bike computer, as a weak real-time system, should be able to process the input between two sensor impulses without any complex algorithms. This means that a very simple, low-cost microcontroller can be used. Another example of an embedded system is an engine control unit for a car. In this example, both the functional requirements and the constraints are much greater than those of a bike computer. Spark and fuel injection timings need real-time calculations to ensure appropriate operation of the engine. Every computation must finish at a defined point in time. Otherwise, the engine will run suboptimally and may even become damaged. The system must also be reliable in harsh environments for relatively low cost and have small device footprint due to limited installation space. Many sensors and actuators have to be networked to the rest of the car and operated by the microcontroller. Consequently, a powerful, reliable, and high-performance microcontroller is needed.
Yeah, that's the end. I'm joking. That's literally kind of person I feel, yo. I never noticed when it ended. The assessment I cannot take because I haven't paid. They tell me to upgrade. Sure. Download documents, trade off for building to see pros and cons. The main advantages of each implementation is highlighted in green. The trade off for building embedded systems. I'm going to say cost. Cost.
Although the term embedded system is typically used for microcontroller-based systems, it is not restricted to just those. Instead, it encompasses systems with as much functionality as possible embedded into few components. This can range from discrete hardware components to fully embedded PCs, while microprocessors with dedicated hardware elements sit in between. Microcontroller-based embedded systems have many advantages. For instance, software-based applications are more flexible than pure hardware and can be adapted more easily to changes in system requirements. This can even translate to better performance and efficiency. By partitioning the system into hardware and software components, the total system cost can be minimized. The system will be cheaper to make, operate, and maintain. Microcontroller-based designs can implement more features. Through system optimization, memory, and on-chip components, redundancy can also be reduced. Finally, microcontroller-based systems are more reliable. Failures can be detected, debugged, and compensated for. However, embedded systems are also subject to constraints. Cost is very important in high-volume production, especially in today's competitive markets. It is important to balance manufacturing, design, and production costs. Device size and weight can be a constraint, especially for portable and wearable systems. Battery capacity is another constraint, which in turn impacts the power consumption profile affordable to embedded devices. Finally, designers must consider the effects of any heating issues that may arise due to a system's operation or the external environment. These constraints have various impacts on microcontroller-based embedded systems, which make operation and interfacing more difficult. For instance, since peripherals are already integrated on the chip, they are usually operated in a way that is unique to every controller type. Although this reduces manufacturing costs, it increases the engineering costs for design, development, and debugging. In other words, the board and design complexity is reduced, but the chip and coding complexity is increased. Programming is mostly done in C or assembly language due to inherent code efficiency and low programming overhead. These languages also allow control of the required clock cycles per operation more easily. Operating systems are less common for embedded systems, although this is changing in the Internet of Things era. Arm Embed OS is one example. OSs can simplify development, but the real-time operating system overhead extends code size and reduces transparency around what is really happening inside the MCU. In summary, in most embedded systems, MCUs are the best choice because they are cheap, flexible, available in multiple configurations, and consume relatively low power. However, they require special development environments as well as support for each processor type for uploading code and debugging.
Like the other processors, like what's the name of these guys? Is it LM? Like those basic processors that use only ARM, mind you, they needed a whole ass programmer. I remember they were telling us, oh, if you want to use, God, I can't believe I forgot the name of this microcontroller. It's very common. They're telling us if you want to use it, that you should come to the department and collect programmer. I was like, huh? When the course that he gave me, I'm not finished understanding. You want me to come and collect programmer? Oh my days. Come and collect programmer, do your projects. I was like, all of us ended up using Arduinos and like super guys. Cause you ask for it. You carry the program and put, I was like, maybe it's because I've never started working, that thing was annoying. So ChatGPT is still cooking. I don't know why it's saying reading on classcentral.com. I hope it doesn't give me like something that is not good. The bad thing about living like in my area, they're always like
the Internet of Things, or IoT, is a special application of embedded systems. A physical device is equipped with a microcontroller, sensors, and communication interface, enabling it to connect with its environment and network with the whole world.
to pray.
The overarching goal of IoT is that everything should be able to communicate with everything. Washing machines with buildings, fridges with supermarkets, personal schedules with traffic management systems. This is a form of ubiquitous computing, meaning that computing is everywhere, not just in our desktop computers. The goal of the IoT and ubiquitous computing is to make daily life more efficient and make better use of global resources. Because virtually any device could have an embedded processor, IoT presents many opportunities for the growth of embedded systems. These can be loosely grouped into three main areas: industrial, consumer, and wearable. The IoT is driven by vast technical development in embedded chips. With smaller packages of embedded systems and more efficient production, prices can drop, allowing the number of applications and systems to increase. Consequently, production becomes more efficient, prices drop further, and units increase. This cycle promotes new opportunities for innovation. For example, smaller chip systems consume less power, creating possibilities for new applications. The number of IoT devices has already surpassed the human population, and huge growth is predicted for the future. According to various researchers, by 2030, the total number of connected devices may reach more than 125 billion. Arm estimates that by 2035, the total number of connected devices will reach 1 trillion. However, there are many challenges to overcome before we can live in an IoT world. For example, as more and smaller devices require chips, chip manufacturing prices need to continue to go down. Chips need to become smaller. Programmers have to work within the resource constraints of embedded devices. As the number of internet-connected devices grows, scalability issues must also be addressed, and the pool of numbers that can be assigned is limited. IPv6 could address this problem, though not all devices have sufficient resources to run an IPv6 protocol stack. Alongside device constraints, data centers and servers must adapt to cope with the huge amounts of data being sent back from these devices. They need to be able to store the data and process it. The underlying network to connect devices to the internet must be reliable. Cloud services must be able to handle large data volumes, process it, and make decisions in real time. All of this calls for more computing power. Even with this infrastructure, devices may not be able to communicate. Right now, we have lots of smart devices around us, but most of them do not speak to each other. This situation is referred to as silos of things. Various technologies are currently being developed to enable devices to talk to each other and exchange data. This raises questions of safety and security. Guidelines to ensure user and data safety, which include tamper resistance, data encryption, accompanying network protocols, and legally binding regulations must also evolve, not only for functionality, but also so users trust these devices. Users are also concerned with battery life and efficiency. Power consumption might decrease as chips become smaller, but battery and charging technologies still have to advance in order to extend battery life and reliably ensure long operating periods. There are also human constraints. Product designers must consider the socio-technical and demographic aspects of the users they're designing systems for. What are the barriers to user adoption or buy-in, and how can they be resolved? The Arm architecture is a family of RISC-based processor architectures, well known for its power efficiency and used in many mobile devices. The architecture details a set of instructions that define how the hardware should work upon execution of certain instructions. These specifications are in place so that software that conforms with them can be executed on any ARM-based processor. ARM architecture is suited for use in an array of IoT applications and includes features that meet the ever-evolving demands for new functionality, integrated security features, high performance, and the needs of new and emerging markets. For example, the ARM v7M architecture, used in the Arm Cortex-M4 processor, is designed specifically for embedded systems and so enables simple pipeline design, low cycle count execution, and minimal interrupt latency, all of which improve speed, battery life, and simplicity of operation in an embedded systems environment. Some companies license the ARM architecture and design their own CPU based on the licensed architecture, rather than using a CPU designed by ARM. ARM architecture also forms the basis for every ARM processor. Although ARM processors are widely considered an industry standard, ARM itself does not manufacture them. Instead, ARM designs the processor cores in its hardware libraries, licenses the designs to producers, and provides an ecosystem of development tools and manuals. Producers combine these processor designs with their own intellectual property or with other third-party intellectual property to create a complete product. ARM's processor technology is designed and optimized with the needs and constraints of IoT devices in mind, and so are more energy efficient. ARM processors cover IoT applications from sensors to servers. Arm Cortex-A processors are application processors used for feature-heavy operating systems and third-party applications. For example, machine learning at the edge, autonomous context-based decision-making, or securely connecting IoT devices to the cloud. Arm Cortex-R processors are embedded processors for real-time signal processing and control applications. They meet the need for high performance, very low latency, and low power in devices such as connected cars, high-end cameras, or disk drive controllers. Arm Cortex-M processors are microcontroller-oriented processors. They can be application-specific or suitable for system-on-chip uses. They are optimized for low energy consumption and small executables, requiring less physical space and silicon for a lower cost. This course focuses on M-series processors. The Arm Cortex-M0 and Cortex-M0 Plus are designed for applications that require minimal cost, power, and area. These processors are optimized for simple sensing and controlling. The Cortex-M3, Cortex-M4, and Cortex-M7 are designed for data-intense operations, with Harvard architecture, dedicated fast hardware multipliers, and math packages. The Cortex-M4 and Cortex-M7 integrate digital signal processing and accelerated floating point processing capability for fast and power-efficient algorithm processing of digital signal control applications.
So we are done with module one. I think I'm going to stop the streaming here, but I'm going to like show you what I would have done if module one was like harder, what I would have done with the ChatGPT summary. So I'm going to go to the ChatGPT summary. And it's not yet done. So we're going to kind of wait for the summary. Meanwhile, maybe I should be answering some assessment question for fun. So we go here, final assessment, final reflection. If I go to, or let me play the introductory material. No. So let's do assessment. Even if you fail it, it doesn't matter. Choose the correct relationship between the ALU, CPU, MCU, and embedded system. So the CPU is a part of the ALU. And wrong. The CPU is not a part of the. Wait, oh. Yeah, CPU is not part of the ALU. CPU, MCU, ALU is a part of the MCU. The ALU is a part of the MCU, which is a part of the microcontroller unit, which is a part of the embedded systems. I think it's this one. How will we even know the correct answer? Identify the correct statements. And embedded systems has a, you know what, this is boring. Okay, so maybe I should play module 2. You said I would have to stop at module 1. Let me see if it's done. It's taking so much time. So I'm going to play module 2 while we wait for ChatGPT.
Mbed is a platform that makes it easy to prototype and develop applications and systems based on Arm Cortex-M based microcontrollers, typically for use in the world of the Internet of Things. The Mbed platform offers a range of features to power developers. These include the Mbed operating system, which is an open-source embedded operating system and includes APIs and drivers for security, connectivity, and input-output. A suite of development tools such as Mbed Studio, which is an integrated development environment for developing Mbed OS applications and libraries. There is also the Mbed Command Line Interface, or CLI, and Mbed Online Compiler, which offer alternate methods for developing with Mbed. A hardware development kit, which is a collection of resources for hardware design. We'll look at the relevant APIs, the hardware development kit, debugging and testing software, and other assets in future knowledge videos. The Mbed operating system, or Mbed OS, is specifically designed for Internet of Things, or IoT devices, and offers a variety of features to enable the development of IoT-connected systems. It provides a layer of abstraction that interprets the application code in a way the hardware can understand. This enables the developer to focus on programming applications that can run on any Mbed-compatible platform. Mbed OS runs a real-time core, or RTOS. The RTOS utilizes abstract data types called semaphores, which manage access to shared resources and synchronization mechanisms, such as locks or mutexes, that resolve concurrency problems. This enables the development of applications with deterministic real-time behavior that can execute multiple tasks in parallel, known as multi-threading. The ARM Mbed OS ecosystem includes many tools designed to work with Mbed OS through the development process. Projects can be created, imported, and built using Arm Mbed Studio, Arm Mbed Online Compiler, and the Arm Mbed CLI. Developers can fetch Mbed OS source code from GitHub and mbed.com, along with dependencies, and compile code for a target board. Mbed Studio is an integrated development environment, or IDE, for Mbed OS applications and library development. The environment includes everything needed for a quick development, debug, and deployment cycle. Mbed Studio automatically detects any Mbed-enabled board or module that is plugged into the host system. It then sources any files required for programming the specific platform, so that the user can focus on their program. The IDE can also flash code directly to the platform. Additionally, the IDE provides a predefined debug profile and can launch a debug session to debug an application. The Mbed Online Compiler is similar to Mbed Studio. It is a lightweight online C and C++ IDE that enables the fast development and compilation of applications, allowing users to either write code from scratch or import existing projects. The online compiler can also deploy applications to a microcontroller. Because it's online, it circumvents the need for a dedicated desktop setup. The Mbed Online compiler requires no pre-installation or setup to work with Mbed, and includes a full code editor, version control, and library management. Arm Mbed CLI is a command line tool packaged as Mbed CLI and based on Python. It enables Git and Mercurial-based version control, along with dependency management, code publishing, support for remotely hosted repositories, and use of the Arm Mbed OS build system. It supports ARM, GNU ARM Embedded, and IAR Embedded Workbench compilers. Mbed provides two security-focused embedded building blocks: Mbed Transport Layer Security, or TLS, and the Secure Partition Manager. Mbed TLS is a protocol for securing communication channels between devices and servers.
So the summary is ready. We're going to scroll up and I'm going to show you, because I don't know if it's with me, but can I listen to all for real? Because if they say a video is 30 minutes, you have to listen for 30 minutes. But if I'm reading and the reading time is supposed to be 30 minutes, if I read it like a little bit faster, so the module one, this module introduces what embedded systems are and why they are important. It covers key characteristics of embedded systems, their benefits and challenges, and it provides context for how they fit into modern computing. Da, 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 da. So an embedded system is a specialized computing system with hardware built around a microprocessor or microcontroller chip. A specialized computing system. So I always repeat it to myself twice, just so that the first one is just for reading, the second one is to understand. So a specialized computing system. So the computing system with hardware, a computing system that is the CPU, ALU, bus, with hardware built around it, with hardware built around a microcontroller, with hardware built around the microcontroller. So the microcontroller is the one in the middle. Unlike a general processing purpose computer, it is designed to perform specific tasks. So an embedded system has the microcontroller with the computing system built around it. Key characteristics: task-specific operation. Embedded systems are typically designed to perform a specific task, which may run continuously, periodically, or trigger their event. They often operate in a loop or respond to external inputs in real time. Hybrid computation. They often involve a combination of digital processing and possibly analog computation or signal processing. So digital processing, analog computation, or signal processing. The hybrid computation means that it can do digital signal processing or analog computation. Many embedded systems interact with the physical world through sensors and actuators. So actuators are like motors, moto, moto, and sensors like ultrasonic sensor, infrared sensor, your camera sensor, anyone, those sensors. Real-time constraints. Embedded systems frequently have real-time requirements, meaning they must respond to events or inputs within a strict deadline. So they must respond to events or inputs within a strict deadline. If I'm going to reform this thing, I'm going to tell you that you should explain it in a way to someone that has never heard of most of these concepts before. I'm going to do that and like download it and everything. But I'm just telling you, like, if you want to do it for yourself, because I feel like things like interrupt, things like underlying things, it should explain it too. So embedded systems frequently have real-time requirements. That's very simple, meaning it must respond to events or inputs within strict deadlines. So they usually have a deadline they have to respond to. Like imagine the weather is like you built an embedded system to detect whether the temperature is hot or cold. So it only has like a finite amount of time to respond. So they always have strict time deadlines. So it has to, because imagine this temperature thing now is for checking someone's temperature, and if the temperature passes a certain level, the person is dead. You need to make sure that it meets its deadline, and it has deadlines to meet. So it needs to meet those deadlines no matter what. A real-time system guarantees producing a meaningful output within a defined short interval. This is crucial in applications like engineering control or medical devices, where timing is critical. Reliability and autonomy. Many embedded devices function in environments without human supervision. So it must be reliable and it must be autonomous. So even if you're not there, your device should do its intended thing. Or if it's going to crash, it should tell everybody, see, I've crashed. The same thing they do for gas. Like gas is not a embedded system, but I'm using it because we all have a gas cylinder, or you've all seen a gas cylinder, except you're super rich. In that case, I'm fighting with you small. So we all have a gas cylinder. So if you notice, whenever your gas is leaking, gas is made with a particular smell that humans can immediately detect, and you're going to be like, that smells like gas. So even if the cylinder doesn't do its job, and its job is to hold gas inside it, there is a fail. So there's something that is going to let everybody know, like, I'm not working properly. You need to come and step in. So it needs to have that. That means reliability doesn't mean, oh, no matter what, even in 100 years it works. Reliability means that even when it doesn't work, it's going to tell you, it's not going to give you false replies. It's not going to tell you A is B. It's going to tell you, I'm not working. Because if you think about it, your body works like that. So they need to handle faults gracefully without crashing. Often, fault handling and diagnostic code is extensive to ensure that the system can recover or alert service personnel of issues. Resource constraints. Embedded systems have to operate under strict resource constraints, often have limited processing power, memory, energy budgets. They are optimized for low performance consumption and cost effectiveness. So if you think about like an embedded system is like just on your table, obviously it doesn't have resource constraints. But when 10,000 people are using that particular device per hour or per second, you have a problem and you need to make sure that it can deal with the task that is given. So a microprocessor CPU is a central processing unit, essentially the brain that fetches. So the microprocessor is just the chip, while the microcontroller has like inputs, outputs, RAM, and peripherals on that one chip. So a Arduino is considered a microcontroller for that reason. While something like, no, I have to remember the name of this chip. I cannot go on like this. Mega. Oh my god. So the Mega, I think, can be considered a microprocessor because Mega just only has those pins. The pins. While a microcontroller, Arduino uses Mega in its pin, and it also has the input. So Mega is one of those chips that requires a programmer because it doesn't have inputs, outputs, nothing. So the programmer imputes things into it, and then the chips like use current to control things. That's why Arduino is considered a microcontroller because it has the Mega inside it, and it also has like a USB port for you to put your USB, and you don't need a programmer in order to program your chip. Embedded systems contains one or more microcontroller, exactly, along with other hardware or software needed to function. You can think of it like the robot vacuums. Those are like they have embedded systems in it. So examples of embedded systems, a bike computer. I don't even know what kind of example that is. Automotive engine control unit. So it is the controls engine functions like fuel injection, ignition time. These are real-time requirements and are strict calculation for spark timing. And fuel delivery must be complete at a precise interval synchronized with engine rotation. Missing a deadline could cause the engine to misfire or damage. Advantages of embedded systems: efficiency, reliability, cost effectiveness. These ones are like explainable to themselves. So IoT, Internet of Things, refers to the network. This is something that has even confused me with IoT, but IoT is not the device. IoT is the network that you use to combine those devices. And to me, that's kind of crazy. Because I always thought IoT, like before I entered uni, I always thought IoT was like the device. But IoT is like the networking, like TCP, IP, those things. That's what IoT is. So IoT refers to the network of physical objects embedded with electronic software, sensors, connectivity, enabling them to connect and exchange data over the internet. Oh my God, what's the one they use for the? Because there's one that is old. IP, I think, is the one they use. That's Internet Protocol, while TCP is Transfer Control Protocol. The exams, the exams, they put us through the girl. The exams where I spent sleepless nights cramming all these things just to come out and have not been able to get a job. I have to do masters to get a job. Let's breathe. Let's breathe. I will breathe in Jesus' name. IoT devices communicate through wired or wireless network, send data to the cloud, directly to other devices. IoT, Internet Protocol. Other things like internet, there's transport network, receiver, transmitter. Which is not funny. It wasn't funny. Connectivity, IoT devices communicate through wired or wireless network. And you know what? I'm rambling all these things. When I was in an interview, tell me why my mind went blank. This guy asked me, "Have you heard of transfer? Have you heard of protocols before?" And I was like, I wanted to cry. I was like, "I've heard of it. I promise you, I went to school." He was like, "What are they though? Take your time." Sir, it's not coming to my mind. Just like, take your time, take your time. I wanted to cry. Oh, God. God. So, IoT characteristics. IoT device communicate through wired or wireless network, Wi-Fi, Bluetooth, cellular, to send data to the cloud directly to other devices. Connectivity allows remote monitoring and control of devices. Sensors and actuators. IoT devices often sense their environment, like a Bluetooth sensor. Bluetooth. I think it's Bluetooth radar. So it sends the thing that is sent from the environment using Bluetooth. So that's, let me not even go down there. IoT devices sense the environment. Possible act on it, essentially bridge the physical world and the digital world. Data cloud integration. So for like embedded systems now, IoT is needed because we're going to use it to send the data to the cloud. So in the cloud, they can run analytics and know, this is where our device is doing this one, this is where our device is doing that one. And that's where you get a data analyst, data scientist to run, you know. Analysis scale IoT is notable for the sheer number of devices from billions today to expected trillions in the near future. These devices range from tiny environmental sensors to smart home appliances. You guys know examples of like your Alexa. That's an IoT application. The networking in it is an IoT application. The fact that you do this and it comes on, that's the IoT part of it. So why ARM for IoT? This is just them advertising their sensors. ARM architecture overview. ARM uses a RISC, reduce instruction set computer architecture. There's T or ISC. There are so many architectures. It's just like this boss, what this logic gate does for this boss. It's not really a logic gate. My diagram was so hard. This results in low power consumption and heat, which is ideal for embedded devices. ARM cores are found in range of offerings from small Cortex-M series to powerful Cortex-A series. This is just them advertising their thing again. Usually runs up to the Cortex-M series is designed for embedded and IoT application. It is low power, small footprint cores, good for IoT sensors and wearable. They execute thumb instruction and usually run up to 550 to 100 megahertz. MO Plus is an even more optimized version of MO for minimal power. Cortex M3, a mid-range core for balancing performance and efficiency. It introduced more features like efficient interrupt handling and decent instruction sets. This is where they are using like M3, digital signal processing instruction, optional flow. I remember when we were learning all this, I was like, where are we going to use this ish? I mean, why I'm seeing it like qualities of a chip, bro. The Cortex M has higher clock speed, dual issue pipelines, DSP extension, and optional double precision FPU. Processor modes and features. ARM processors typically operate in single main mode plus an interrupt handler mode. They have a hardware stack for interrupts, making interrupt latency low. Um, so they are just advertising their this thing. That's the end of module one. So this is what I usually do whenever I'm reading. So you cram all that write up, the video makes so much sense to you. The write up is so simple. Now I'm going to try to simplify it even further. So the write up is going to be even simpler. So this is how I would simplify it. Like it never fails when I tell you to like edit it in a way for someone that just finished high school or secondary school. So essentially all you would know is Ohm's law by that point. And it will give it to me. And I hope to see you in my next video. Bye.